In this session we will introduce a particularly elegant method for analyzing the Schrodinger, or STI, Schrodinger time-independent equation for the case of the simple harmonic oscillator. So it's almost in code now. So the quantum mechanical simple harmonic oscillator Schrodinger time-independent equation is this. So this is a bit of revision from earlier sessions. Right? Here's your Schrodinger equation for the case of the simple harmonic oscillator, where your z was just a substitution for your x, just a constant times x, and your eta here, eta epsilon. So, I must take a mental note. How do you pronounce this symbol? Anyway, eta epsilon, whichever, is defined as the energy of your oscillator divided by h bar omega. All right. Now, towards the very end, around here, of the previous session, I introduced so-called ladder, like climbing a ladder operators of this form. There were two of them. And A plus, I've just written here in shorthand instead of writing out two of them. But so just A plus is defined, 3 bars defined, as d by dz minus z, and A minus is defined as d by dz plus z. Okay. Now I ask you to do this as homework using these ladder operators. So the plus ladder operator is usually called the step up, because you're stepping up a ladder, right? The step up operator, and the A minus form usually called the step down operator, right? And generically, collectively, the two of them together called just ladder operators. Now, using these ladder operators, the step up or the step down, you can generate the Schrodinger equation, this, for the quantum mechanics, the Schrodinger equation for the simple harmonic oscillator, SHO. Okay, so I ask you to do that as homework. So what you're asked to do is to show that you can rewrite this, the Schrodinger equation for the simple harmonic oscillator, in this form and this form. They're the same. Well, this is equivalent to that, and this is equivalent to that. So you just have two different ways of writing the same equation. Okay, so actually plug in A plus, so you get d by dz minus z. So here you put d by dz minus z here, and differentiate the u by this and minus zu, and then get that result, and then apply A minus to it. So then whatever the result is from A plus u, then apply the operator A minus, which is d by dz plus z, and you'll find that this is equal to that. And similarly for this. So here you apply the operator A minus on the u first, right? So A minus would be d by dz plus z, and so on. Do that as homework and show that this and this is just the same as this. Okay? Now, so what? Why do that? Well, if you can start rewriting your Schrodinger equation for the simple harmonic oscillator in this form and this form, these two forms allow you, in a sort of quasi-algebraic way, to calculate, to solve this equation effect. In other words, to find what are the allowed energies, what are the eigenvalues of E here, and what are the eigenstates, the eigenfunctions, the wave functions, u, right? So, if you can solve that, and we did it before with the Hermite polynomials and so forth. So the previous technique. So all this session is in a sense an alternative technique to solving this simple harmonic oscillator SHO Schrodinger equation. Right? But it's hugely more elegant. It's quite breathtaking. But by the end of this session, if you've understood it, I hope your jaw will be dropping something. Saying, "Oh, how nice! That's really nifty." So the person who discovered it deserves a medal. Although I suspect it probably, elements of it came out, like the stepping up and stepping down technique came from mathematicians. I think a French mathematician, I think around about 100 years back, a century ago, and the theoretical physicists picked it up, but maybe picked it up independently. I don't know. I just don't know enough of history of how, at this level of detail of how it actually arose. I guess I should learn more history of the development of math. All right. Okay. So do it as homework. Show that this and this are both equivalent to this. They both give you this equation. All right. So assume we've done that. So we can work with this one or both. So if we can solve these, we can solve what the E or epsilon, the epsilon here and the U are. That's what we're trying to do. We're trying to find the eigenvalues and eigenfunctions of the Schrodinger equation. So either using this way or this one or both. In fact, we'll do both. Right? We'll use both. Okay. Now watch the really nifty trick. What you can do. Take the equation asterisk circle, this equation, which I've marked here. This is just an identifier, well, just to, so you can, talking about this particular equation. All right. So take this equation and multiply on the left-hand side. Sorry, multiply on the left of both sides of this equation by a minus. So in other words, you take this equation and you multiply here on the left by a minus, so here a minus, and here a minus. Well, this is all a constant, let's say, so well, actually we can put the a minus here, to the left of the u, right? So, well, here's what here's the result, right? So you've got an a minus here, so here. So a minus a plus a minus u equals all this constant stuff, and then an a minus a u. Right? Now you can rewrite that as now this a minus u. Let's rewrite that as just u dashed. Okay? And this a minus u, the same thing on the right hand side. Write that as u dashed. Okay? So if a minus u is rewritten as u dashed, you get this equation, right? So you rewrite that as this equation. Now, so we've got a u dash now, and our eta epsilon whatever, we can relabel e dashed, and if you'll notice that e dash is just well, I'll call it epsilon eta. I'll call it eta for the moment. Eta dashed is just eta minus 1, right? So written in this form, which is just a rewriting of this, written in this form, this, I mean, have a look at it. It's the same as this equation, and I've got as an identifier here. I've got this sort of kind of triangle circle thing. So there's just an ID, an identifier for this equation. Okay? So this a dash a plus u, sorry, a minus a plus u dashed. Now this equation here is just the equivalent of this one, right? So this equation is equivalent to the Schrodinger equation. So we have now another solution, right? Because this gives, you know, for a different energy. Now that E dashed is different from E. You know, E dash is, I'll just call it E. E dash is just E minus 1. So that this E dashed here, that energy is different. So we've got different energy, different eigenvalue. And we've got U dashed. That U dashed is a solution to this equation, right? But this whole equation is just the same as the Schrodinger equation. So we now have another solution, a new solution, U dashed, with a different eigenvalue, different energy, different allowed energy, E dashed. Okay? And this energy E dash is one less than the previous one. Okay? Now, if you keep doing this multiple times, and effectively you're stepping down, and that's where the term came from. So by applying this A minus on the left-hand side, on the left, on both sides of your equation, you get, each time you do that, you get this new solution to the Schrodinger equation with a new energy. And each time you do it, each time you step down, right, your energy goes down by 1. Your E goes down by 1. And so if you do it n times, you'll get